with the split of it. Okay, that's the time. כן, בסדר, מה שיצא, אוקיי, נו, בצורה הבאה. רגע, זה רק הדף הזה? לא, בדיוק, אוקיי. טוב. Okay, so what I'm going to tell you now, we're going to summarize what we've studied so far by another example of a model, of a neuronal model, okay? Of what? Neuronal model. Model of a semi-linear neurons. I'll tell you exactly what is semi-linear. But since we are dealing with linear algebra, we'll just consider the linear part, not the semi-linear, but not the part it's not linear.
Example of what?
Example. For everything we've studied, it's a combination, it's a linear, it's going to be a network of neurons, a model of neurons network, which we're going to solve using linear algebra tools we have, okay? I don't mean it to resemble anything of the physiological world at the moment, okay? I'm just going to show you a model. I'll tell you what are the neurons, how they are connected, what is the dynamics, and what is the solution, we're looking for, and how to solve it analytically using linear algebra, okay? So, the neuronal models so I'm going to model of neuron network, that's what I mean. So we have semi-linear neurons, this is what I'm going to describe, and there's a network of these neurons. Okay. So the neuronal models are semi-linear. What does it mean? Okay.
Don't forget to write big.
What?
Don't forget to write big.
And write big, right. Okay. So the neuronal models are semi-linear in the following sense. So suppose I have the x-axis is going to be I, and you can think of I as the input, but we can think of it as the current, which is also represented by I. So give it any interpretation you like. This is the input, the current delivered to the neurons, and this is, we're going to call it F. This is going to be the activity. So again, you can think of F as a frequency, like a firing rate, or you can think of it as a voltage of the neurons. Let's think of it as firing rate versus input current, okay? So the neurons are silent, they don't fire until the current reaches some threshold T, larger T, and then from that point the firing rate of the neuron is growing linearly. Okay? That's all we have here. Okay, and theoretically in this neuron there's no limit to how abrupt can be the firing. You can fire at as large rate as you want if you give it large enough input. Okay? Usually there are some rectification or some limits to the firing, but this is not going to interest us now. Yeah. It's not a stupid. If it's a question, it's not stupid. Ask it.
You don't know yet. When you say linear, you necessarily mean straight line?
Right.
Okay.
Okay. So this is the dynamic range. This is the dynamic part. It is linear. Okay. I'll write a formula for this, and this is also linear, right? It's also a straight line. Here you have nonlinearity. That's why it's called semi-linear. So up to one point, it is linear in all different ranges. Okay. So what? But what do you mean it should be? Okay. This is what we're going to solve. We don't know how to solve exponential. This is you solve with Dana exponentials. With me, you solve linear stuff. Okay. So let's write down the equation for this. So f is going to be some beta. Beta is the slope of this line. This is called the gain. Okay. Beta times what? Times I. But minus t, right? Only after t we start to be linear. And how do I take care that if I is less than t, so we get 0, so there's a way you can just write plus here. Okay? Okay. So this plus sign means the positive part of what is written here in the brackets. Okay? So when you take some function or number and you add this plus here, it means that it's going to be f if it's greater than 0, and it's going to be 0 if it's less than 0. Or you can think of it as the maximum between f and 0. It's the maximum. If it's greater than 0, it's f. If it's negative, it's 0. So what does this mean? That if I is greater than t, you go according to the linear rule, beta times the current. And if I is smaller than t, you didn't reach threshold yet, so this becomes 0, and everything becomes 0. So that's how you write. This is the nonlinearity, this breakpoint that is imposed on the neuron. Okay. So this is how the neuron behaves. And what we're going to assume is that the neurons that I is large enough, so it be in the linear part. Okay. This is how it's symbol. Okay. So I being large enough, I mean that the input soon the input will see. No, soon we'll build a network. Soon we'll build a network, right? And in this network, this I is going to be written in some terms that are relative to the network. Okay? In some parameters, we're not going to use I. That I is going to have some components. Okay? And there's going to be some expression here representing I. And we're going to assume that we are in the dynamic range, which means that the input is large enough so that all neurons are active. What?
Bigger than t?
Yes, bigger than t. Okay? Yeah, right. That's what's written here. If I minus t is what? In the graph, yeah, before t is 0. This is 0, yeah, okay. Yeah, it's because I wanted to differentiate the two. Okay, this is 0, okay? It's inactive until it reaches the threshold. Okay. So, I told you about the neurons. Now I want to build a network. What do I have to tell you? Right. I have to tell you the connectivity. First of all, I have to tell you that there are networks. That there are many neurons. Okay. Okay. So now take how many n? Okay. N such neurons. Okay. And the connectivity will be all to all, which means that all neurons are connected to all other neurons, except that a neuron is not connected to itself.
Same measure?
Soon, that is. So the connectivity matrix is now just going to tell you what is it's going to be a 1 and 0 matrix, connected or not connected. Yeah, C is zeros on the diagonal, as always, and ones elsewhere. Okay. Now, I want also to have a strength for the connectivity. Okay, I don't want, as we did before, that the strength is 1, and you get large inputs, and then you have to threshold them. I want, in advance, to make the inputs normalized in a way. So, therefore, we're going to, this is C, this is C when it only represents the connectivity. But now we're going to write a different C. We're going to think of C as the one that represents the strength of the connections. Okay? So if you represent the strength, so it includes representing the connections, because if the strength is 0, there's no connection. Okay? This is just representing the connections. So now we want to represent by C the connectivity strength, and it's also going to be uniform for all neurons, and it's going to be in a way that it all sums up to 1. So the strength of all connections will be, so we call it J, and it's going to be some moment. Okay, some J tilde over n minus 1. Okay. What I mean by that is that the strength is some value that is divided by n minus 1, so that when I add all the connection, or add all the inputs, I get, it's independent of n. I don't want the input to be dependent of n. If I take a larger network, 10,000 neurons instead of 1,000 neurons, I don't want the inputs to increase in 10 and the firing rate to increase in 10. I want everything to be normalized according to the number of neurons. So, what? So, in terms of all connections will be J, this. So, this means that C So C is the following matrix. This is the connectivity matrix. It's zeros here and J elsewhere. This means that all connections are uniform in strength.
What is
J
J tilde?
tilde is what I mean is that there is some value, you think of it as the connectivity, right?
It's randomized?
No, it's uniform. There's no index I and J here, right? All connections are the same. As you see, all connections are the same. The parameter is J tilde. J tilde is the parameter you determine to say what is the connection, what is the connectivity strength. But I want the real connection to be whatever parameter you chose divided by n minus 1, so that the network, the input won't be dependent of the number of neurons. Okay?
What does it exclude? Every parameter can
Right,
show
right.
S divided by n minus 1.
Right. Okay. No, but the thing is that if you now going to take the same J, the same number you got J equal 7, okay? And now you're going to increase the network to a network of 10, you're going to increase it tenfold from 10,000 neurons to 10,000 neurons. I don't want the connectivity strength to remain 7. I want it to be normalized, okay? So that's what I say, whatever you take, you determine J tilde, and then the model tells you what is J. You determine J tilde, and the model determines what is J. You take J tilde and divide it by n minus 1. There are other models when you can divide it by square root of n minus 1, stuff like that, okay? This is what the model states, that all connections has to be normalized by n, right?
So the capital J on the left, that's a general measure, which shows the property without the connection to the size parameters. It's a bit like...
No, the J tilde is something that tells you about the connectivity strength. In this...
Which one depends on the size of the network? The J or the J tilde?
This one depends on the size.
So the J tilde...
J tilde you determine, and then tell you take the same strength, but take a larger network, so J tilde won't change, but J will change because you normalize, so that the sum will be, if you sum all these, you get something of the order of J. If you sum all these, you get J tilde. That's the thing. If you sum each row, you get J tilde. Okay? Right. Okay. Yeah, right. But sometimes the weights are not uniform usually. Not all to all usually. No. This what makes it linear. What makes it linear? Okay. So what makes it linear is the fact that this is going to be so we're going to multiply, as you know, the matrix by the linearly multiply the matrix by the state. This is one thing that makes it linear, and the other thing is the neurons themselves that are the dynamic range is linear, not exponential. The neurons, where are the neurons? This makes it linear. Okay.
This is the neuronal
Response. This is the response function of the neuron.
Yeah, you say it's like neuronal range.
Dynamic range. I mean, this is the dynamic range. This is where it's dynamic. What? Yeah. Greater than I is greater than T. Okay. So, so now we can basically start to do what we're doing. You can start off with some state and multiply the state by the matrix C and get the state at the next time step and multiply it again and so on, and to see where the network evolves to. But I want to start off with a silent state when all neurons are 0, okay? But if they're all 0, so nothing is going to go anywhere. So what can I do? We're going to also add an external input, something that is constant and independent of what happens to the neurons. Okay, so at every time step there is going to be also an external input. Okay, so there is also an external input. We're going to call it IX. Okay? And this is also going to be uniform to all neurons.
Every time step?
It's constant, yeah, to all neurons. Okay, so let's call it a constant external input, IX. It's uniform to all neurons. Okay, so now let's think what is the input to a neuron. Okay, so the total input to a neuron is, okay, so let's call it I, the input I to neuron I, what is it? Is the I external plus C, right, times the state. Okay? So what is the state? Let's write it down explicitly. The state is the activity of each neuron. We called it F, right? F1, F2, to Fn. But what is C times all this? Just summating, each of them is multiplied by J, except for the ith element. So how many J times F we have? We have n minus 1 such. Right. Okay. So this is multiplying the ith row of C by this column. So it's J F1 plus J F2 all the way to J Fn, only leaving outside J Fi, right? Because it's not connected to itself. Now, think of it that if we start off with an initial state that is the same for all neurons, let's say 0, so at every time step, each neuron gets the same input. At the first time step, this is 0, and all of them get only I external, and they are all the same. And the next time step, here they are all the same, so it doesn't matter which I took, you just take n minus 1 times this F and multiply it by J. And again, all of them are going to be the same. So if we start off with the initial state that are all zeros, at each time step, this multiplication is going to be the same. So the input to each neuron is going to be the same, and the frequency, the response is going to be the same. So they're all going to behave the same way. Okay. Or you can think it by symmetry. All neurons here are the same. They see everything the same way as any other neuron. So there's no reason for one neuron to be more active than any other. If neuron number 1 is more active than neuron number 2, why is it so? They all get the same input. Everything is, and then this is only assuming that we started off from the 0 state. Yeah.
Why didn't you add I external to I minus C? I plus I external minus C.
No, this is the input.
Yeah, I know.
When I subtract T only when I calculate the response.
No, but every neuron feels this I external. So why don't you plug it in there?
Yeah, soon you'll see that it's practically the same.
Okay.
That's right. Like The t serves as an attenuation of the external input, right? We'll see it in a moment. Yeah.
Why are we using the entire matrix and not just the row of I as the input of neuron I?
Right. It's not. It's right. Thank you. It's C. This is. So we have to take the ith element of this vector. Okay. Thanks.
So we just calculated the ith row.
Right.
Times
Yeah. So the ith element is the ith row times this. Okay. But if the initial state assume the initial state is all zeros. It's not a necessary assumption. If you also assume that the initial state is random with mean 0, like you take the initial state to be some random number with mean 0, so or with any mean, it doesn't really matter. You take the initial state to be some random number, so they are all averaged by some mean. So in each row, you get the same after very little, very few time steps, if n is large enough, of course. Okay, so assume the initial state is all zeros. Then all neurons have the same output f, means fi equals f independent of I, and the input is also uniform, and what it is, so I is not I, it's just I, independent of I, which is I external. And so what is this calculation going to be? It's n minus, it's all the time is j f1 plus j f2. It's n minus 1 times jf plus n minus 1 jf. And here we get again the j tilde, right? Because j is j tilde. I remind you, okay? J is j tilde over n minus 1. This is the normalization takes place. So it's I external plus j tilde f. Okay, so I'm just going to write down what is the activity f of the neuron resulting from this input, and then I'll tell you what is the question we ask about the network, and we'll answer it in the next class, next hour. So this is the input, and this is going to determine the output f of the neuron, of each neuron, at the next time step, right? So we can think of it as f in some time step t. And now let's see what is the output of the neuron. And I'll tell you why I use the same letter f. Okay, so the output is therefore I remind you we have the now we are going to impose the semilinear function. So f is going to be beta, and now we have the input. This is the input, I external plus j tilde f, and we just take the positive part. What? Come again? We started off with the all zeros because not only all zeros. If you start off with any random state, but with if you choose it independently, so they're all going to summate to the mean. But if you start off with, let's say, the states, I don't know, 0, 0.1, 0.2, you divide the n between 0 and 1 or 0 and 2 or whatever. You divide it in some way. So not all neurons are going to see, not all of them are going to see the same, right? Neuron number 1 is going to see the activity. Let's say let's say have 10 neurons. 5 of them are in the initial state. 5 of them are zeros, and 5 of them are ones. All right. So the neurons 0 to 5, 1 to 5 are going to see 5, and neurons 5 to 10 are going to see 4. So maybe later on it might average down. I should think about it. It might be independent of the state, but we assume that we start off with a 0 state. Okay. It might be that it's not really important. Anyway, that's right. I thought I forgot something. Thank you. Minus t, right? Okay. Here you go. Okay, so why am I using the same f? Because this is to tell you about what we are interested in. We are interested in what are the steady states of the system, to what state it evolves after some time. Okay? And that's why I'm looking for not every f. I'm not interested in what is f0 and f1 and so on. I'm interested in some f, some particular f, maybe there are a few of them. What are the activities f such that I start off with neurons that are active to the level f, and after I iterate it, I stay in the same place. Okay? This is called a steady state. So in the exercise you did earlier in the MATLAB, there were two steady states, all zeros and all ones. Okay? That's what now later on, maybe not in this course, but you understand this has something to do with the properties of the connectivity matrix. So now that I think of it, it's indeed independent of the initial state. Okay? I correct myself. It's independent of the initial state. It's something that has to do only with the connections, some properties of the matrix, which I'm not going to discuss now. But there are steady states. In the example you solved, it was all zeros or ones. Here, we'll see that there can be another steady state. Okay, so next we're going to solve this. This is very easy. This is just one equation. And after solving this, we'll go to a more sophisticated network, and there we'll have two equations, okay, or more equations. Okay, so now let's take a 10 minutes break from 6 minutes to 12 till 4 minutes past 12. And אני חושב את הכלב זה נורא מספר I. כלב זה נורא מספר I, והשלמה זה מטריצה כפול המוגן, כמו שעשית במחשב, עשית מטריצה כפול, זה היה מטריצה וזה היה הממוצע. זה סטייט, נכון? אז זה המטריצה האפשרי, זה הסטייט, זה מה שמחשב לך את הכלב, לפחות כמה שהחלק שלו שנוצר מתוך הקלטים האפשריים, אבל אני מתעניין רק, אז זה נותן לך וקטור, כן? נקרא לו S1, לא S, כי זה לא היה סופי, נקרא לזה משהו ביניים, U1, U2 עד U1. מה? כן, זה כאילו S בזמנתי, לא, S בזמנתי פלוס 1, זה כשאני אפילו זה, נכון, כמו שאתה את המצב, אתה הפעלת את הסף, נכון? כדי להגיע למצב החדש. נכון, היה לך איזה חישוב, ואז בדקת, אני עבר את הסף, לא עבר את הסף, בלי לקבל את החישוב הזה אחד. אז פה, זה עדיין לא נותן לך. זה רק נותן לך את הקלט, זה הקלט החיצוני, זה הקלט הפנימי, נקרא לזה, ורק אחרי שאתה מפחית מזה את הסף, מפעיל לזה את הזה, אתה מקבל את S בזמן T פלוס 1. אז זה תוכן המצב בזמן T.
אז זה סקלר, זה יותר את זה ברור.
כן, זה בעצם סקלר, נכון? זה מטריצה כפול וקטור, אין לך וקטור, אבל אתה בוחר רק את האיבר ה-I, כי זה מה שתורם לך.
אבל יכול לחשוב על זה גם כמספר של שורה בעמודה, שורה שלו בעמודה.
כן, אז האיבר ה-I זה או פשוט לקחת את הוקטור ולקחת את האיבר ה-I, או פשוט לכפול רק את השורה.
אוקיי, למה הלאה קורה?
אוקיי, אז זה הקלט, כמו שאמרנו, כמו שבמחשב, כשעשית במטלב, אתה לקחת את הקלט, אבל בדקת כל אחד אם הוא עבר או לא עבר את הסף, וזה מה שיקבע לך את המצב הבא. אז עכשיו גם כן, תצטרך לעשות אותו דבר, פשוט יש לך נוירון אחר, זה לא סתם סף, אלא יש לך, זה הקלט, כמו שחישבנו אותו. דילגנו על למה זה הקלט, כן? אז לכולם יהיו כל הזמן באותו מצב.
רגע, אני מניח שכולם על זירו?
בוא נתחיל בכולם בזה שכולם מאפס, עזוב את המקרה הכללי. כולם מאפס, כן? אז בכל שלב כולם רואים אותו דבר.
אז זה לא יתקדם לשום מקום, אני לא מבין.
לא, יש לך את האקסטרנל. הוא מגביר לך, ואז בשלב הראשון יש לך רק כולם על האקסטרנל, זה הקלט שלהם. נניח שהאקסטרנל מספיק גדול כדי שהם יהפכו להיות פעילים, אוקיי? זה חלק מההנחות. אז האקסטרנל הופך אותם להיות פעילים, דוחף אותם לאנשים.
אז זה אומר שאם עושה אינסוף איטרציות, אז נגיע לאינסוף כאילו בה?
לא, זה העניין.
זהו, אבל הרעיון שזה כן נסחם כל פעם מחדש.
כן, טוב, במקרה הזה...
אפשר להגיע לאינסוף, אתה אומר?
לא, המקרה הזה היא חייבת שהאקסטרנל... צריך לחשוב על זה רגע. טוב, אנחנו נראה מה צריך להיות הפתרון. רגע אחד.
זה סתורו של רם?
כן, נכון. קיצור, אז...
לא, זה קראתי עליו, כאילו, היה לי טעות, כאילו...
על מה? במה?
5.
עכשיו כאילו?
כן, לא יודע, כאילו, משום מה, זה לא
זה טעות חישוב, זה ברור.
כל הזמן טעות חישוב, איזה 3 שעות, לא יודע.
לא כתבתי זה היום? לא כתבתי
הוא מדבר על הבוחן עכשיו שהיה כאילו?
לא, הוא לא עשה את זה, אבל שהיה אמורים ללמוד לזה, של 5. רגע, בואו נמשיך רגע.
כן, אוקיי. אז בכל אופן, אז בואו נגיד אנחנו מתחילים מאפס, כן, אז זאת המקרה הכללי. לא מתחילים מאפס, אז אחרי שלב אחד כולם יהיו ב-I, ואחר כך כולם יהיו ב...
לא, עכשיו חשבתי שם.
יש משהו שיצא מזה, כן? אז בשלב הראשון כולם יהיו ב-I, כן? ועכשיו, כולם כבר נותנים, יש לך גם את האקסטרנל, וגם כולם נותנים קלט אחד לשני, כן?
אוקיי, שהוא I.
שהוא, מה?
הוא I?
לא, כן.
הוא I אקסטרנל?
לא, I...
כאילו, יש...
כן, כן.
לא, אז תפסו, כמה רוצים לחשוב שזה.
זהו, אחר כך. אז עכשיו מה יהיה הקלט? פה, זה יהיה הקלט, כן? יהיה קלט, כן? עוד קלט שכולם יקבלו, כן? אז יהיה J כפול... כן, בעצם זה J כפול האקסטרנל, נכון? שלב ראשון כולם יהיו באקסטרנל, ואז יהיה לך האקסטרנל ועוד J כפול F, כן, שזה J כפול האקסטרנל, אוקיי?
אוקיי.
אוקיי, להביא לכם שאלה?
כן, אז J...
זה לא חתום במקרה.
אוקיי, אתה יכול לחשוב על זה, זה בעצם תהיה, לא חושב, תהיה... לא יקרה, מדהים. אז יהיה לך האקסטרנל, אחר כך יהיה לך באמת J טילדה כפול האקסטרנל.
למה זה טילדה?
לא, כי שחמת את זה, כי אתה מקבל N-1 כאלה מכולם, ו-J הוא מנורמל, אז יהיה לך J טילדה כפול, במקרה הזה, בטיימסטפ הראשון זה יהיה האקסטרנל, נכון. ואז אתה עכשיו, זה המצב, עכשיו רגע, זה לא קובע את המצב של כולם, נכון? זה רק קובע את הקלט שהנוירון מקבל. כדי לדעת מה המצב החדש שלו, צריך לקחת את זה, להכפיל ב-C, להכפיל בבטא, או להכפיל ב-T, לראות שזה עבר את הסף, ואם זה עבר את הסף, להכפיל בבטא.
אוקיי, אז F הוא פשוט כאילו, כמו שאני אומר, מספר הפעמים שהכפלנו את I.
לא. כי הנה, עוד פעם, ה-F הראשון הוא 0, אוקיי? אחרי טיים סטפ 1, ה-F הוא לא ה-external, הקלט, האינפוט הוא ה-external. האינפוט הוא ה-external, אבל מה F? F זה ה-external מינוס T כפול בטא, זה F. עכשיו יהיה לך איזשהו F, הוא בעצם יהיה אותו F לכולם. ומה יקרה בטיים סטפ הבא? עוד פעם, ייכנס לכל תא, הקלט של כל תא יהיה ה-external, ועוד JT זה כפול F, מה שהוא יצא, זה רק הקלט. עוד פעם, תיקח, תפחית את T, אם זה גדול מ-0, תכפיל בבטא, זה יהיה ה-F החדש. קשה קצת לצפות, זאת אומרת, קשה לצפות מה זה בדיוק יהיה כל פעם, אבל מה שאנחנו כן נתעניין, וזה מה שאמרתי, אנחנו נתעניין בלאן הכל הולך. אנחנו מחפשים איזשהו מין steady state, כן? מצב שבו לכולם יש את הקלט הזה, והקלט הזה, אתה מכפיל אותו ב-J טילדה, מוסיף לו את ה-external, מוריד את T, מכפיל בבטא, ואתה חוזר להיות אותו F. אז גם, מאותו רגע, הרשת כבר לא תשתנה לשום מקום.
ועכשיו היא תמשיך להיות אותו דבר לכל הנוירונים, לא?
זה תמיד יהיה אותו דבר לכל הנוירונים. אבל השאלה היא אם בטיים סטפ הבא זה ישתנה. אז עוד פעם,
מתי לא תשתנה, אתה אומר?
כש-F יהיה כזה, כן? F יהיה כזה, שתחשב לפי F את הקלט, ולפי הקלט תחשב את המצב החדש, זה יישאר באותו מצב. F שיפתור פה איזושהי משוואה. אז זה יהיה רגע שלנו יבוא, אני חלק לכולם.
אני יותר גדולים שיסתכלו לטיעונים שלך.
כל מי שפה כבר לקח את שלו? נראה למה?
כן.
אוקיי.
גם עכשיו הייתי אותך שיגיעה אותי, אמרתי לא אומן, כאילו, שאלה קלה. מה, איפה? הבמה, אני חושבת את הטרמינטה, ואז אמרו, אני לא חושבת, אני חושבתי לשאול את הטרמינטה הזה, ללכת ל10 דקות, ועוד ב5 עשיתי את כל השאר. אז היה לי תמיד שאלתי על חישוב כבר, וזכרתי בהרבה דברים, אני הבאתי כל דבר, מה על חישוב? זה לא יכול להיות חישוב. וכאילו, כדי לעשות בזמן, אם זה נראה לי להיות כמה זה 10 דקות? לא יודעת, לא הבנתי. אמרת את זה גם אז.
לא באמת, לא.
בוא נחכה ונראה.
לא, בשאלה אחת פשוט ניחשתי. כאילו, אפילו לא ניחושים מושכלים, פשוט היה שלם חסר, גם עכשיו היה קל, היה הוגן ואפילו קל, אבל אני פשוט לא הייתי תוכן. אני לא מאשים אף אחד, זה היה הוגן וקל, אבל לא הייתי תוכן.
אני חושבת שדווקא בוחן לזה מעצבן. הקודם? עוד עכשיו? לא יודעת, זה כאילו נכנסו לכל הנוירון כמעגל חשמלי, אז אתה יודע, זה חוק של התנגדות. שאלה על זה. כאילו, הבנתי שזה בכלל לא קשה, אבל זה חוזר את החומר. אני מוצאה לי. לא, צריך לדעת החומר. זה כן. לא, כאילו, אני יודעת, שאתה חוזר מאוד טריקי או לזה. להמשיל להם את
זה ידע.
שאלות אפשר לא שאלות ממש קשות. אבל כן, החומר גם ככה...
תשמעו מה קורה כשמתחילים מאפס.
האמת היא, אתה לא חושב שזה.
הגענו לכאן. זה מתאר רק את האיטרציה הראשונה. זה לא מתאר מצב קבוע נמשך לאורך זמן.
כן. זה... אולי למדתי את זה. לא, למדתי את זה תמיד הרי אמרנו שאנחנו נשארים כמו 3 סוגים של פאצ'פלט. סוגים וזה נכנס פנימה. לא למדת את זה? יש אפילו יותר מזה. לא. אתה מדבר על על הכלב.
אבל זה השלב הראשון. נגיד אם יש לך אפס בהתחלה, אז כולם את ה-external.
כן, אבל יש לך פה זה, כאילו פה אתה אומר אחרי, לאורך זמן, כאילו ממה שנראה לי, בפעם הראשונה הקלט של כולם יהיה, כאילו זה 0, ואז הקלט היחיד יהיה ה-external. ואחר כך, בכל תא הזמן, אתה מוסיף כאילו ה-external פלוס n-1, j-f.
כלומר, בפעם הראשונה נגיד שאני מריץ את זה, אני מוסיף ה-external פלוס זה. נכון?
כן. ואז וה-f הוא 0, ובגלל זה אתה מוסיף רק 0.
רגע, למה ה-f הוא 0?
כי ה-f זה הפעילות שלנו. במצב הראשוני, כאילו 0 הוא 0. אז ואז יהיה לך ה-external ועוד n-1, j, ה-external.
נכון.
ואז כאילו זה בעצם נותן לך כל צעד. הקלט שהמערכת מקבלת בכל צעד
הבנתי.
זה קלט קבוע.
אבל ה-S עצמו משתנה.
נכון.
אוקיי.
S עצמו משתנה, אבל כאילו זה תמיד נראה ככה.
הבנתי, יפה. כאילו, כן, נכון. מה שלא חשוב זה שה-F הוא לא תורם קבוע.
כן. אחר כך כאן הוא השאיר אותו F, בעיקרון יש לך, ה-S צריך להיות לו אינדקס זמן.
בדיוק.
T0, T1, T2, כאילו
פה
F זה ש-T.
זה FT וזה FT מינוס 1.
נכון, אבל בכוונה אמר שהוא משתמש באותו F, כי הוא רוצה להגיע למצב שבו FT מינוס 1 יהיה שווה ל-FT.
מה לא לעשות את זה? כאילו לא לעשות בכלל את זה?
בואו, אני לא חושבת שזה נכון.
כי אני חושבת שבא לי למרוד.
לא, אחד נכון. זה נכון, זה
כי לא אמרתי.
בסדר. אבל אחר כך אמרנו משפחה לא כזה, אבל אין שום סיבה שאני אבדוק את זה, כי בדור שלי יש שאלה מתנות הרבה שלושה בנים ובדור שלי בן ועוד סבא שלי יש 5 ילדים. אבל ברור, כאילו זה גם לא מעניין לנו כאילו לא, אבל מוסיפים להם עוד 3
תנו לכולם תמיד כולם נעימים וכל אחד נעימים וכל אחד יש עניין לראות לא, צריך לשאול אותו, אני חושבת שאין לו מבחן בדיוק
אני רק מקווה שהציון שלנו לא שווה ל-66.
מה לא?
2 שפול עם 100.
כן, 2 שפול.
מה, אבל היה לך טוב אתמול לבוא לזה? נראה לך?
לא כל כך.
לא?
נו, מה אחד להגיד? אתה אחרי שתי?
פשוט חשבתי רגע לפני המבחן, ואז כאילו למדתי לראשונה מה הקשר בין קוטר וזה. זה היה כאילו קצת מוגזם שאני לחשוב שאני אזכור את זה, אני אוכל לזכור את זה השאלה כאילו
You will lose it at 5. לא, אבל אני יודע שברגע שמורדים וזה רגע עם 0.1 out of 6.
זה ברור שעד גיל שנה נשארת בבית. כן, אני מתארת כאלה.
מה עשיתי מבחן זה לא שם?
אם זה רע, שזה כבר נדע, זה לא מדבר,
יש לי רגע שאלה, למי שיש שיעור אחרי השעה הזאת? אפשר? לאף אחד? חושבים להציע לו להוסיף מתישהו איזה שעה ולבטל את הקיצור של ההפסקות.
לא, יש, לי לא,
פעם אחת להוסיף שעה.
אז אולי אבל לא מיד אחרי, אפשר לקבוע שעה אחרת.
אין לך זמן אחר?
לא, אני רוצה רגע לעבור על הטכנולוגיה, אבל כאילו אבל הרעיון טוב.
לא חוזר זה לא כזה שונה. Okay, one comment about the solution to exercise number 3, the one you submitted last week. So question 3, you had to characterize the linear system according to parameters A and B. You remember? There was something with A equal B different than 0, not different than 0, something like that. So there was a typing error at the framing of the question, which made the question much more difficult than it intended to be. So you didn't have to submit it, but I want to tell you that I will correct the solutions, the file of the solution, but it's not that I'm going to correct it towards what I'm not going to leave the question as it was and give the new solution for the much more too difficult question that it became. I'm just going to change the question, but I'm going to do it only in the solutions file. Okay, understand what I say? So there was a mistake in the question. In one place there was written 1 plus b y, and the solutions are as if it read 1 plus 2b y. Okay. In this way, the question is interesting enough and reasonable. With this, what you have to solve, it's too difficult. It's again nothing that you can't know, but it becomes too difficult. Okay. So I'm going to correct the solutions file, not to give you the true solution for this, but rather to change the question to this. Okay. And leave the solution as it is. And the second thing is that you had to convert some 4x4 matrix. And I don't know if you looked at the solutions already or not, but if you looked at the solutions for the conversion of the 4x4 matrix, it's incorrect. Okay, the first row there is incorrect, and when you multiply, you don't get the identity. And thank you for all the ones who submitted the full solution so I can see. So this is also, if you look at it by now, you should look at it again. I'll correct it. The first row is a mistake. What you did is correct. What? It's exercise 3. It's all exercise 3. Okay. So where were we? So we're looking for a solution. Okay. So now, assuming, and later on we'll see what we have to assume in order for that to happen. Assuming that all neurons are indeed active. So if it all depends on the I external and on the J. Okay. If it happens that the I external, suppose I told you we start off with a 0 initial state. So if the I external is too low to pass the threshold, so nothing is going to happen. Even in the first time, after one time step, it's all going to stay 0. So indeed, F equal, if I external is too low, so F equals 0 is the F equals 0 is the steady state, because F equals 0, this is 0. If I external is less than T, this is going to be 0, and that's going to be 0, and nothing is going to change. But we assume that neurons are active, that I external is large enough for the neurons to become active, and then we want to solve this, assuming the neurons are active. The steady state solution is, so let's write again the equation, is when this is satisfied. F equal beta I external plus J tilde F minus T. Okay? This has to be solved. This is linear, and I write down the solution. You just separate F and do all the to do. I'll leave it here so you can, just a moment. I'll leave it here so you can see. Okay, so the solution is F equal beta over 1 minus beta J tilde I external minus T. Okay.
Solution for what?
What?
Solution.
The steady state solution. What is the steady? This is the steady state equation. Okay, let's call it. This is the steady state
It should be smaller or equal to 0.
equation. doesn't change. You start off with, you get to some S, and if you iterate once more, S doesn't change. So this is called a steady state. It's never going to change. And the solution is the steady state solution. The F, what is the F that satisfies this, and this is the F that satisfies this. So, what does it mean? It means that if I give you now, I tell you, what is the model that is, what is beta, what is T, and I tell you what are the connections, which means I tell you what is J tilde, and then tell you what is the external input, what is IX. I give you all parameters, and then you plug it all in this equation, in this formula, and this gives you the steady state solution of the system, okay? Which means that this is what the system is going to evolve to, and I'll give you an example. Okay, so example. So let's think of something interesting. Let's build a nice example. Let's see B1, and I external, let's have it 2, and equal 2, and so this is going to be 1, and now let beta be 3, and of course there are some constraints here. This part of the idea. If the constraints are not going to be met, it means that this assumption that all neurons are active is not going to be met. For instance, now I take beta equals 3, if I take too large J tilde, so this becomes negative, but it can't be that the state is negative. So I have to, yeah.
Beta depends on the number of iterations?
No, beta is, all these are parameters of the neuron. I remind you, the neuronal model has the parameters beta, the gain, the threshold T, and that's it. The network model has the parameter J tilde and I external, and that's all the parameters.
Okay.
So beta is the same. This is the gain of the neuron. The slope is beta.
Okay, so
Nothing.
to the steady state, it's independent on number of iterations?
Okay, so what do you mean independent of iteration?
No,
You can ask yourself, how many iterations do I have to go through to get to the steady state?
Okay.
So there are examples in which you get to the steady state in one time step. In one time step, you get to the desired depth. There are other examples in which you never get to the steady state because you only approach the steady state is here, and you only approach it asymptotically at infinite times. You're going to get to the steady state, but the steady state is never reached. Actually, you just approach it. Okay, so
why does it a solution? What does it mean?
okay, you agree that okay. Check that this is the solution of this. Okay, this is the solution of this. Okay, I just separated S and set S in one.
To be a solution?
What does it mean that it, again? What does it mean that S? What does it mean that I found a solution? Again, what does it mean to be a solution? Is to be some activity level S, such that if you calculate the input according to this S, this is the input according to this S, and then how from the input you interpret what is the activity, you subtract the threshold and multiply by beta, and then it happens that you get again the same S. So this means that all neurons are active in a way. You have a state. And if you now impose the next time step and calculate what is the next activity, the activity next time, you get the same activity. And it means that it's never going to change, because if it didn't change today, it won't change tomorrow.
Why is it an assumption that all neurons are active?
Because you can assume that all of them are inactive, And okay, 0. They are all 0. I external is not large enough, so they don't become active. I remind you here there's no limit for the activity. It's unlike what we did last time, that the activity was either 0 or 1. It's not that you're limited, the activity is not limited by 1. It can be anything. Okay? As large as you want. Okay, so now let's take beta equals 3, and now, and let J be J tilde, so it'd be easy to calculate 3 over 2. No, 2, רגע, אני רוצה שפה יהיה, אני רוצה שפה יהיה, 1 לא יוכל להיות פה, אבל נגיד יהיה פה שליש נגיד, אז 1 פחות 2 שליש אני רוצה, וזה 3 עד חצי, לא חצי, 3 חצי, זה 3, אני רוצה שזה יהיה חצי, אז צריך 1 פחות חצי, זה צריך להיות חצי, 3 כפול מה נותן לי חצי? 60, אוקיי. Okay, so under this, now don't calculate, let's see to what it evolves. Okay, so let's put it here, and now let's see how the activity evolves in time. Maybe it will make it clear.
This equation is not the equation of the entire line, just for the steady state, just for one.
This is this equation. This is the steady state. This calculates f at the steady. So let's look at the example, and I think it will make everything clearer. Okay. So at t equals 0, we are all 0. Okay. So now we don't have to consider all of them. Let's just consider one of them because they all have the same activity. Okay. So at t equals 0, f equals 0. Okay. So and what is the input at time 0? Is just the I external, right? I follow. Where was it? It's late. But it's written here. Okay. This is the input. I external plus J tilde F. Okay? So IR is I external plus J tilde F, but F is 0, so I just have I external, which is 2. Okay? And now at T1, how do I calculate what happens at T1? So F, I remind you, is beta I minus T, which is 1. So it's beta 3, and I is 2, minus 1. So the activity is 3. Okay? And now what is going to be the input at the next to the next? So it's going to be I external 2 plus J tilde 1 over 6 times F. So it's 5. No, 2.5. This is the input. Input at time 1. Okay. Moving to the next time step. T equal 2. Okay? So, what is the F? It's beta I minus T. So, beta is 3. Input is 2.5 minus T. So, it's 3 times 1.5. It's 4.5. We're reaching there. Where do we expect to get? Oh, we don't expect now. It's a razor now. We'll see where we get. is external plus j tilde f. אוקיי? 9 חלקי 2, 9 חלקי 12, זה 3/4 is 2 and 3/4. Very little increase in I imposes very little increase in F. Okay, we reach time equals 3. Okay, so now all this is done in milliseconds by MATLAB. Okay, you understand. What you have to do is to build something like this and
it's not supposed to be 2 and a third?
2, למה? זה 9 חצאים חלקי 6, 9 חלקי 12, 9 חלקי 12 זה 3/4. 2 ו-3/4. Is it?
כן.
Okay, just by the way, so what you will have to do, you will build something like that in MATLAB, and at each time step, you'll see what is the activity, and you will be able to follow the activity according to time, and see it approaches at finite time or infinite time to the expected limit, to the expected steady state, and you will jiggle it with the parameters to see what can happen. Okay, so input is 2 and 3/4. Okay, so F, again, beta is 3 times 2 and 3/4 minus 1 is 1 and 3/4 times 3, 5 and a quarter. Okay, and now the new input is 2 plus 1/6 times 5 and a quarter, אז 21 חלקי 4, 21 חלקי 24, 7/8, so it's 2 plus and 7/8. You may guess that the input is approaching 3, okay? And then, at t equals 4, where we are, f is 3 times 2 and 7/8 minus 1, okay? So it's getting closer and closer to 2, and this will get closer and closer to 6. Now, you can realize that it's never going to, this is never going to become 2, and this is never going to become 6, okay? So now 1 and 7/8, so it's just like 3 minus 1/8, so it's 6 minus 3/8, so it's 5 and 5/8, and next time step is going to be closer and closer to 6, okay, and I, and so on. So we have a hunch this approaches 6. Let's see what the... Is it supposed to be 6? Or is our hunch wrong? Let's calculate. F is 3/1 minus beta over 6 times I external minus 1. Yeah? This is half, this is 6. So the steady state is 6. So this is, at the moment, this is what the network is going to be at t goes to infinity. And when I say t goes to infinity, it includes many cases. Either it happened, if it happened on some finite time step, so by this equation, since this solves whatever equation it solves, it's never going to change anymore. And in this case, it's just going to approach this limit. Yeah, your question.
If it's linear, it's not supposed to be like constant, like between t equals 2 and t equals 3, it's not supposed to be like...
A constant increase?
Yeah.
No, it's not constant. It's not linear because you have. It's linear, but it's not homogeneous. Okay, that's what makes it inhomogeneous. Okay, it will be homogeneous if it indeed be linear in time. But since you have here the I external, so we don't have a homogeneous increase. It doesn't. At 0, it wasn't 0. The I external. Okay, so it's just a little shifted, and that's why this is also. But no, the increase is not going to be constant at every time step. No need for that to be. Okay. Okay. So now I'm just going to describe the equations of something more complex, but I'll let you. Maybe I'll solve them. Okay. We'll see where this evolves at infinite time. So now assume we have something a little more, just a little more complicated. We have two populations, excitatory population. So what we all discussed till now is all excitatory. What makes it excitatory? That all connections are positive. It means that if you're connected to me and you are active, so I'm going to feel you as something that raises my activity. And the inhibitor is going to be negative connections. Okay? So till now, it's just as if we discussed an excitatory network. And now we're going to add an inhibitory network. So what does it mean? We have n. Let's, for now, assume it's the same n. Did I assume it's the same n here? Yeah. I have n excitatory neurons and n inhibitory neurons. And again, all the connectivity is all to all. All excitatory neurons are connected to all excitatory neurons. All excitatory neurons are connected to all inhibitory neurons, and vice versa. And only the strengths are going to be different. Okay, so I'm going to mark it this way. I have, from excitatory to excitatory, I have some strength J, E, E. I remind, too narrow. Okay, so I erase this N. So from excitatory to excitatory, I have some strength. This is just marking the strength. This means there are connections, and the strength is some J, E, E tilde. And I remind you, this is going to be normalized by n minus 1. Okay, so J, E, E is J tilde E, E over n minus 1. And also the inhibitory neurons are going to have some J, I tilde. And they're going to be connections between the populations, J. So this, from excitatory to inhibitory, how do I call it by convention? IE or EI? It's IE, okay? The index on the right, it's the same as in the matrix. The index on the right is the presynaptic, and on the left is the postsynaptic, and this is JEI. Okay, so what? The right, J, A, B, this is the pre, and this is the post. Okay, this is the convention. Because it's the same way in the matrix. What? This is from E to I. This is from I to E. Okay, so, and what else we have? We have external input. Again, constant for each population. So we have I external E, and we have, maybe different, I external I. So remember to differentiate between the I which is the current, and the I, which is the inhibitory population. Okay. Now another convention. What means that this is inhibitory? That the connections are negative. So the convention is the following: that the J's are always positive numbers. Only when I add them as the current, this is going to be with a minus sign. Okay, but the J's are all JAB is always, it can be 0 if I decide there are no connections. These are all non-negative. And the negativity of the inhibitory input is just going to be in the formulas themselves. So what is the, we have the neurons. So A and B is going to stand for either A. When I say A, it means either inhibitory or excitatory. So what is the output of neuron from population A? F neuron I from population A. What is it going to be? It's going to be the gain, the same way, the gain, but I don't want, they all have the same gain, but it depends whether they are inhibitory or excitatory. So it's the gain, the common gain for all neurons in this population, and there is the input to neuron I minus the threshold, which again is going to be uniform, not for all neurons, but for all neurons in the same population. So it's going to be this. So it's the same. As I told you, what I did before is just everything was here. It was this, and this current, and these connections, and this external input. Sorry. A, yeah. So again, this means that all neurons are uniform in their parameters. In the same, all neurons in a population have the same parameters, but I might have different gain for neurons in different populations and different threshold for neurons in different populations. E or I, right. So A stands for either E or I. So A is either E or I. But then you can think of making it even more complex if you have few excitatory populations and a few inhibitory populations and so on. You can make it as complex as you want. Okay, so now let's see the equations that are met here. Yeah. In this, the connections are going to be all to all. Everything is going to be uniform. Yeah. This is the basic concept we're dealing with here now. Connectivity matrices which are all ones except for the diagonal, and the J's that are normalized by n-1 and so on and so forth. Okay. So there are some little details here. The J's should be normalized by n-1, and here also n-1, but this should be normalized by n because it's all to all. And you can have different numbers. You can have NE and NI, but it doesn't matter what is the number of neurons because everything is normalized. So the input is going to be the following. The input to an so I write it E because it doesn't matter which neuron I'm looking at. All neurons see the input the same way. So what is the input to an excitatory neuron? So it's the I external of the excitatory, right? What does an excitatory neuron get from his excitatory friends? He gets JEE times the FFE, right? Plus JEE, no, the F, you may have two different F's, F for the excitatory and F for the inhibitory, plus FE. But again, it's going to be the same F for all neurons, for all excitatory neurons. And what a neuron here gets from his inhibitory counterparts? Minus JEI till multiplied by the activity of the inhibitory population. And what is going to be IE? I for the inhibitory population, I external for the inhibitory, plus, now, first of all, let's do what he gets from his friends. So it's minus J I tilde Fi, and from the excitatory, he's going to get plus J, just a moment, J I E F E. And what was the question? Where is T?
No, why it's J tilde, not just J?
Again, you can call it whatever you want. When I say tilde, I mean the unnormalized value. And when I say J... What? No, this is, I remind you, what is J tilde Fe? It means that I took the connectivity matrix and multiplied. So I had n minus time, I summated n minus 1 times the activity of all neurons, but the connections are normalized by n, so that's why the n is gone. It's independent of n. That was the idea of the normalization. And now, what are the steady-state equations? Now, from this input, I can calculate the activity, right? I can calculate the activity at the next time step, but we're interested in the steady-state solution. So let's write down the steady-state equations, which means that F is going to be equal to the F calculated by this input. F is equal the input calculated by the same F, right? So let's write it down and be clearer. These are the inputs. The steady-state equations are, okay, so Fe, I want Fe to equal the activity calculated by input Fe and Fi. Okay, so they're going to be coupled. Okay, so Fe is going to be beta E multiplied by input minus threshold. So input we have here, I external E plus J tilde E F E minus J tilde E I F I minus threshold of an excitatory neuron plus. But then again, we are going to assume that all neurons are active, so I straight away erase this positive part and just hide this. It looks very scary, but think of it. It's all linear. It's a Fe, and here we have a coefficient for Fe, and the coefficient for Fi, and some coefficient which is not connected to any of the variables. So think of it as an equation with variables Fe and Fi. Two variables. Till now we have one equation, and whatever is not connected to any of the variables is going to be on the right side of the equation. Yeah, it's going to look like A11 Fe plus A12 Fi equal something. This is how we can formulate it. Everyone sees how we can just change a little, gather everything that is Fe, everything that is Fi, and have coefficient for Fe, coefficient for Fi equal B1, some number. And Fi is going to be beta I external I plus J. Now I just want to be here, I want to have Fe, so I write it J tilde IE Fe minus J tilde II Fi minus Ti And this is, with many parameters, a system of linear equations, two linear equations in two variables. This is one variable, Fe, and Fi is the second variable. So now I'll show you how it looks after you make it into, to give it a matrix form. This matrix form. A, 1, 2, Fe, plus A, 2, 2, Fi equals B2. So now we're going to show you how it looks like in the matrix form. You're still going to see it. Don't worry. The corresponding matricial expression is one minus beta E J E E beta E J E I, and here we have minus beta I J I E, and here we have 1 plus beta I J I Fe Fi equal beta E I external E minus TE, and beta I external I minus TI. Phew, much simpler. Now, okay. So this is what?
Supposed to be JT?
It's all JTL, right? So let's call this matrix A. This called the vector B. And this you can call the vector F. F equal B, that's what we are. And we know already how to solve it. And if it has a solution, right, we can calculate the determinant to see if it has a solution, unique solution, or not. Okay. In some cases, there might be a range of steady states. Okay. Now, if you have the numbers, you can, in this stage, plug in the numbers. If you don't have the numbers, so you can just calculate it, for instance, by Kramer's rule. Okay, this is a rather convenient way when you have so many. Like, you're not going to apply row. It's going to be difficult to apply row operations on this matrix. Rather, it's going to be fairly easy to calculate the solution according to Kramer's rule. So we have a condition for the solution. If determinant of A is non-zero, we have a unique solution. And we can calculate it by Cramer's rule. So now I wonder if I want to write it down or not write it down. Let's just write one of it to find. So I'll just give you the formula for FE. Okay, and I'll show you. I just want to analyze it a little and compare between FE this time and FE we had before. So FE in the steady state is the following. No, it's not. I didn't do some manipulation earlier. Okay, so let's bear it. Anyway, it's something you can just calculate. Okay, just you remember Cramer's rule? Okay, it's the determinant of you divide by the determinant of A, and then you substitute this column by the B and calculate the determinant, and so on. It's rather a complicated expression, and there's some manipulation I didn't do before, and I don't want to do it now. So anyway, it can be solved rather easily, and then again, also here, you can really visualize. You can take or get parameters and visualize how it evolves in time to the steady state. Okay. So now let's take a break, and then we start off with new theoretical stuff, which practically has no connection for a few moments to what we did before.
מה הולך להיות החומר על כל זה? איך אפשר במטלב? מה הולך אפשר בכל זה?
אין לי תשובה לשאלה כרגע.
עשינו את הפונקציה של הדטרמיננטה, עשינו את הפונקציה של הדטרמיננטה, ניתנו תופעה קצת מוזרה. שונים נתנו תשובות שונות לזה, כאילו, לזה תשובה לעבוד, זה מאוד מוזר.
אנחנו לא מקבלים השתתפות, אבל הם כאילו, זאת אומרת, חלק ט' נותן ניסוי מכונן.
מה, זה נורא נמוך? זה נורא קטן? אי במינוס...
אבל זה שונה
לא, כי זה תלוי...
לא, כן, תבינו. שזה יוצא לכם אי במינוס 12?
נכון.
תחשבו את זה בידנית, אתם תקבלו 10.
ברור, אבל מצד אחד אתה רושם כאילו האם הוא שווה שווה ל-0 אומר כן, הוא רושם את השעות האם הוא שווה שווה ל-0 אומר לא.
לא, אני הייתי שנה ראשונה.
מה, איזה מה זה? כן, אז קודם כל מג'יק, מג'יק עם ארגומנט זוגי תמיד יהיה, אוקיי?
לא, אין לנו בעיה.
אני לא יודע למה, אני לא יודע איזה כלל שמג'יקים של ארגומנט זוגי תמיד 0. לא, זהו, אולי ככה בחרו את זה, אני לא יודע. אני לא יודע. מג'יק שלהם? לא, כולם זה מג'יק. לא יודע כמה זמן אגב אחרי, אז תקרא, אני אצטרך תחרות בין הסטודנטים יעשה את זה הכי... אני יודע הכי מלך חשוב את 10 על 10, משהו כזה. כן, כן, 10 זה פורקי אחרון. עושים את זה ריקה. מה שלב לוקח לו? כן, זאת אומרת, מה שאתם עושים, שהמקוד שלנו עושה 10, מה שאתם עושה 7,000, כן? אז העניין הזה של המג'יק, או בכל מקרה, מטריצות היא דטרמיננטה נורא קרובה ל-0, בקיצור, אני לא יודע בדיוק מה אתה עושה ולמה זה קורה.
לא, כאילו גם, לא רק זה, גם שזה היה במג'יק אי זוגי והיה על זה פתרון, אז זה היה אותו פתרון, זה נראה אותו פתרון, אבל הוא מציג אותו, הדט של מטלב מציג אותו ארוך יותר עם יותר איברים.
אוקיי, והדט שלכם?
והדט שלנו...
תסביר הדט שלכם, היא אמרה שיש אי קוהרנטיות בין דטים.
לא, וגם בין דטים השני.
קודם כך, באותו ורסיה של מטלב.
וניסינו לשחק... לא, אבל אם אנחנו מגדירים לו, אני יכולה להגדיר לו לונג, כאילו אנחנו
שינינו פורמטים.
שינינו פורמטים, זה עדיין מציג את זה אחרת.
קיצור, אנחנו לא יותר.
אבל אתם בטוחות שזה היה בדיוק אותו...
זה לא אותה פונקציה, זה לא העניין.
לא, מה?
לא, אז אם שאתם חישבתם. אתם מדברים על איך זה יכול להיות שדט של מטלב במחשב B נתן ערכים שונים באותה מטריצה.
אולי באמת זה גרסאות שונות
של מג'יק?
של מטלב? לא, של מטלב.
אוקיי, ואז זה אתם רואים אחרת?
אז למה שלנו לא מציג את זה באותו פורמט כמו זה?
מה זאת אומרת?
כאילו איזה סיבה יש אם אני מגדירה פורמט למטה, אז למה זה לא מציג את זה אחיד? כאילו למה, וגם הוא לא מזהה את זה כזהות. כאילו כשאני עושה לו שווה שווה, הוא לא מבין שזה אותו מספר.
מה? על
הדף
מציאות מה? על
שלי?
מציאות גדולות?
לא. כאילו כל מיני, שיחקנו עם זה, אבל
אוקיי.
לא...
טוב, אני לא שיחקתי עם זה עד כדי כך. אני לא יודע. כלומר, צריך כאן קצת יותר להבין בקרביים של מטלב, שאני לא מבין, בשביל להבין את זה.
אולי הם מגדירים בתוך...
אז לא, אז קודם כל לא הבנתי, את מבקשת אותו להציג דף באיזושהי רזולוציה מסוימת?
אני נגיד קובעת לו פורמט...
אבל אני לא יודע מה הוא עושה עם זה, אולי הוא לוקח את המטריצה והופך אותה לפורמט הזה ואז הוא חושב. אני לא יודע.
לא, אבל לא משנה, כל עוד הוא
כל מה
מציג...
שמעת.
אבל אולי בתוך הפונקציה של דף שלהם יש... צריך לקרוא את זה.
אי אפשר, זה העניין, אי אפשר לקרוא את זה.
כן? לא מאפשרים?
באמת?
זה אחד מכם אמר לי, דעתי אותו בעניין הזה. אני לא יודע, מישהו אמר לי בשבוע שבועיים האחרונים שדף זה... זה לא פונקציה, כן. אבל אני מניח שגם אם...
כן, זה לא יעזור.
זה לא נראה לי שהדף שלהם זה משהו שבאמת עושה איזשהו חישוב סטנדרטי. אני מניח שהוא יותר גדול, אני נכנס לזיכרון ויודע כאילו... אני יודע יותר על איפה דברים יושבים בזיכרון כדי לחשב את זה, כי באמת אני רואה שזה...
אין לי טוב, אבל לא חייב ונשלח לך.
לא בסדר, תשכחו, אני הולך לבדוק את זה כמה, כי אני הולך להסתכל על הכל, אני לראות שהוא סביר, אני עושה את העבודה.
כן, אבל גם יש מבחנים את זה, לא?
הקרובה הולכת להיות בשעה אחרת.
כן. אבל באופן חד פעמי?
נראה לי.
כן, חשוב מה נעשה את זה.
תסביר רגע. כאילו מה הולך פה בעצם? זה קשור לזה, וגם זה נותן לו, וגם זה נותן לו?
לא. כל אחד מהנוירונים האקסיטטוריים, החוזק שנכנסת עם האקסיטטורים עצמו הוא J, כן, אבל בעצם JE, וזה נותן לו, JI נותן לו JEI, ובלי קשר, I external זה בלי קשר נוסף.
אני שואל אותך שאלה, אבל תעשו כל ההפסקה. אמרתי, סוף שיעור. יש לי שאלה כללית, אבל שאלה כדאי לדבר עליה בשיעור. אתה תגיד אותה מסודרת, עניתי על שאלות.
Okay, as now for something completely different. We're going to discuss now some theoretical concepts, and eventually everything are going to collapse together to known to known terms. Okay, so linear space. So a lot of things we did are part of, or because of things we discussed, belong to some entities called linear spaces. So now I'm going to give you an abstract definition of what is a linear space, and then we'll see examples, and we'll start to develop the theory of linear spaces. What is important about the definition is that the definition I'm going to give you has no context. It's an abstract definition. What it means, it tells you that if a set of elements has a list of properties, then this set is called a linear space. Okay? But the important thing is that the definition has no context of itself. And the idea is that we have an abstract definition, and then we can look at one set and say, oh, this is a linear space, and look at another set and say, oh, this is a linear space. And everything we are going to prove about linear spaces will be true for all linear spaces. And it's going to be a general proof. And everything we go in the street and meet a linear space, we can know that everything we proved about linear spaces is true for the one we met. Okay? So we don't have to prove separately the theorems for each linear space. We prove things generally for linear spaces. Anything that has the list of properties, whatever we prove is going to be true for. And this is how we deal with, understand abstract definitions. Okay, so a set V in which there is a binary function. We're going to think of it as summation. A set V in which there is, so a lot of things I'm going to write down and then I'm going to explain. A set V in which there is a binary function and a multiplication with elements from R that satisfy now leave about 10 lines is called a linear space and over R. Okay, so what did I write? I didn't say anything yet, but this is how it looks like. So what do we need to have a linear space? I want to tell you about something that is a linear space, what do I have to tell you? I have to give you a set V of elements. These elements can be anything. It can be numbers, it can be chairs, it can be students, it can be anything. Just need a set. But what do I have to have in this set? I need to have a binary function. What do I mean a binary function? I think of summation. Each two elements of the set, I can sum them together to get something. Okay? Like I can sum two numbers to get a number, and I can sum two n tuples to get another n tuple, and so on. But a binary function for now, it can be any binary function. You can think of matrices and multiplication of 2 by 2 matrices and multiplication of matrices. It's also a binary function. Okay? So soon I'll tell you what this function has to obey, what rules it has to obey, and then why we call it summation. But for now on, it has to have a binary function. Binary of each two elements. Each two elements have some solution of this function upon them. What else do I have to have? A multiplication with elements from R. So first of all, this is the only thing that is going to be not abstract in this definition, and it can be even more abstract because it don't necessarily have to be from R, the multiplication. But we're going to discuss only linear spaces over R. Maybe I'll give you one or two examples of linear spaces over C, the complex numbers, but for our course, all linear spaces are going to be over R. So what does it mean? It means that for every element in V, and for every scalar in R, I know what is the multiplication of the scalar with the elements. Okay? This is a multiplication with elements from R. So I have a set, I have two operations defined, and now I'm going to list you a set of rules that if all are obeyed, then I call this set together with the operations a linear space over R. Okay. Okay, so what is a multiplication with elements from R? It means for every element in V, I know what is, and for every alpha in R, I know what is alpha V. There's some function that tells me what is alpha V. Okay? V can be a set of students, and I know what happens when I summate every two students. I get some other students. I know the one sit next to them, or in the middle between them, or close to the median line of, I don't know, whatever. And I know what is the multiplication of scalar alpha with every student. Alpha times the student is, I don't know, the score I got in course alpha, whatever. And this is the operations. Now, if these operations are going to obey the rules, I don't know yet because I didn't tell you what are the rules. But then you'll find out, okay, that the set of students with what I defined is not a linear space. But I can define something else that is a linear space. Okay? What are the rules that has to be obeyed? So I have rules for, the function, I'm going to denote it by plus. Okay, so the plus rules. Okay, so one is closedness. Okay, V1 plus V2 has to be in V for all V1 and V2 in V. Okay? I cannot summate two like odd numbers cannot be a linear space because when I take the sum, odd numbers with regular summation. If I sum two odd numbers, I get an even number, and it's outside of the group. If you add two elements, you have to stay inside the group, the set, not the group, the set.
Binary function has to be summation.
I mean, a binary function, I denote it by plus, and we think about it as summation because what it obeys is something that we think of as summation. Okay? Usually, in our examples, it will be indeed summation. It will relay on summation from R. Okay? But it's not. Basically, it's not necessary. As I said, you can define the summation of two n tuples in many ways. We define it in a specific way, and we'll see that what we defined really makes the set of n tuples a linear space. And we can define it differently, and maybe it becomes a linear space, maybe not. It depends on what you define. Okay, so it has to be closed. כן, סגירות. It has to be commutative. V1 plus V2 equals V2 plus V1 for all V1, V2 in V. Okay, so this is going to be in the end of, we're going to have a lot of rules. Not 3. Associativity, and practically anything I told you about n-tuples. V1 plus V2 plus V3, if I sum the first one, it equals V1 plus V2 plus V3. Okay, the fourth rule is the existence of zero element.
This is not part of the plus rule?
Yes, it's number 4 of the plus rule. Existence of zero element. Of zero element. Let's call it A, such that A plus V equals V for all A in V. Now, why don't I call the zero element 0? What? No, so soon I'll denote it by 0 V, like the vector V. What? No. So 0 V is going to denote the zero element in this linear space. Why don't I call it from now 0? Why don't I give it a special notation? When do I give something a special notation? When there's only one, when it's unique. Now I don't demand it to be unique. The fact that it is unique is going to be a theorem about linear spaces. But the idea is that the constraints I impose on the set should be minimal. If I can prove from only these rules that the zero is unique, I don't need to state it as an axiom. Okay? I don't need to demand that it be unique if it's anyway going to be unique. Okay? And existence of opposites this means that for any V in V, there exists a U in V such that V plus U equals A, where A is a zero element. And then again, I don't call this U minus V yet because I don't impose its uniqueness. Later on, I'll prove its uniqueness. And then I'll say, okay, the opposite is denoted by minus V. So this is the summation rules. Now I have another operation, the multiplication by by a scalar. Also, I have rules for this. Yeah.
Rule for it, is it for all V and V, not for all A and V?
Here?
Rule number 4.
Number 4. For all V and V. Sorry. Okay. Is it clear? Great. We move on. Multiplication rules. Rules of scalar multiplication. Okay, so again, it has to be closed. Alpha V has to be in the big set V for all alpha in R and V in V. Some kind of associativity. So I discussed it a lot in the first lecture. So alpha B, if I multiply first in R and then by V, it has to be equal if I multiply alpha by the vector VV for all alpha beta in R, V in V. Now we have two rows of distributivity. So, distributivity 1 means that alpha V plus U equal alpha V plus alpha U for all alpha in R, V and U in V. And the second distributivity rule is distributivity over summation in R. Alpha plus beta V is alpha V plus beta V for all alpha beta in R, V in V. And rule number 5 is called rule of unity. So in R, there is the unit element, which is 1, and it has to be that if I multiply an element in V by 1, I get V back. Okay? So the unit element is the element which is neutral in multiplication. It has to be neutral also in scalar multiplication. 1 times V is V for all V in V. So these are the rules that have to be obeyed, and I'm not going to, you don't have...
Because it's 1 now.
What? It's in R. 1 is in R. There's no unit vector. Okay, so when we have a linear space, the elements of the linear space are called vectors. So, and now after this, you have to reach the line, then V is called the linear space over R. Linear space is also something called the vector space. Okay? And the elements in V are called vectors. I the elements of a linear space V are called vectors. Okay.
The one here is one, color one?
Yeah, one in R. There is, and I can call it this way because I know there's only one.
Unique.
Yeah, it's the unique unit element in R. Okay, so now examples. So R2, the set of all two elements vectors, is a linear space over R. This is the general case. This is part of the general case. If I write here n instead of 2, so I get x1 to xn, x1 to xn in R is also a linear space over R. This is what we discussed till now. This is the main linear space we saw till now. And it's just an example for a linear space because there are many other things that are linear spaces. Okay, so for instance, M 2 by 3 over R. Okay, the set of matrices of 2 by 3 matrices with elements in R. Now, it's not enough, as I told you, to say what is the set. I have to tell you what are the rules. But I already defined, you know how to add together two matrices and how to multiply. So now we're going to talk with the regular. Yeah. But the important thing is to realize that I have to tell you what are the operations, what are the summation, and what is the multiplication with the regular operations is a linear space over R. So in the first lecture, when I defined all the new operations and I showed you about some of them and told you all the rules they obey, in fact what I showed you is that these sets are linear spaces. Okay?
Each element, the vector is called vector?
No, I don't call it a vector now, right? Rn is a set of n tuples, and now that I know that it's a linear space, so I can, okay, these are vectors.
X itself is called vector?
What is x?
X, Y.
No. X, Y are in R. Let's discuss R2.
No, it's
Let's discuss R2, okay?
you say the elements are called
Of a linear space V are called vectors. The elements from R are not the elements in V, in this case. Elements in V is R2. Elements in R2 are called vectors. The elements in R are scalars.
Elements here called vector?
No, so when I say element, so the set of 2 by 3 matrices, you know what, I expect you to understand it when I say the elements of the matrix. So sometimes it's called entries. Entries of the matrix. Because if the word element confuses you, so when I say entries of the matrix, I mean what is written inside the matrix. Each matrix is an element here. Arachim, values, whatever word. When I say the elements of a set are the
Special case of the
No. A set, this is an element of the set. X is an element in the set X. But when I talk, so if I take this matrix, it's a 2 by 3 matrix. It's an element in this linear space. Now, when I talk about matrices, so how do you call the 1, 1 element, the 1, 2 element? These are also the elements of the matrix, but they don't belong to the matrix. The matrix is not a set. So distinguish between the elements of the matrix, the entries of the matrix, the values of the matrix, and the fact that the matrix is an element in the linear space. It's a vector. That's why I want to call it a vector now. So you say, now we're going, don't ask, it's a vector or it's a matrix. A matrix is a vector in this vector space. A vector is not an n-tuple. N-tuple is not a vector. N-tuple is a vector here. And the matrix is a vector here. Okay? Now, some other examples. In case things were not confusing enough as to what are the vectors and what are the scalars and what are the elements, note that R is a linear space over R. Okay, so now think of R as the set of elements. These are going to be the vectors, and we know how to add two elements in R, which means we have this summation operation. And on top of this, we think of another copy of R as the place for all scalars. And we have a multiplication of each element here in the vector space with a scalar. Right? It happens. And it happens to have all the rules. The summation is commutative and associative, and we have a zero element, and so on and so forth. And the multiplication is distributive. And so note that if you think of R as a set that is the candidate to be a linear space, and you think of the regular summation and multiplication with elements from R, think of it as another copy of R, which is the set of scalars, and you find out that all rules are obeyed, and by definition, R is a linear space over R. Okay? Yeah?
So, in order to be defined as a linear space, something to be defined as a linear space, it has to have at least two elements in it because of the binary function?
No. You drive me. You drive me to the next example I anyway intended to give you of a linear space with one element, and there's only one such. So this is one example. Now another example. Right. So I call it zero. Okay. Think of it as the element zero, but it can be any one element. But this one element is necessarily will have the job of being zero. Okay. So think of one element zero. Okay, is a linear space and is called the zero space. Okay. Now, why didn't I tell you what are the operations? Because there's no other way to define the operations. First of all, what is the summation? 0 plus 0. What can it equal? It has to be 0. It has to be closed. And for any scalar alpha in R, what is alpha times 0? Okay, it's 0. Okay. So, as I told you, it functions as 0, but I can take as that's what I mean. You have to distinguish between the contents and what the definition tells you to have. I can take a candidate student who wants to volunteer. Okay, Orly. I can take Orly and think of the set of Orly, right? With the following operation: Orly plus Orly is Orly, and for any scalar alpha, alpha times Orly is Orly. So this is a linear space. It has all properties as the zero space. That's why we call it the zero space, and that's why we call it the zero space, because there's only one such. There's only one way to define the operation. There's only one way to define the multiplication, but any one element set with proper definitions, and again, the only way to define these operations in a closed way is going to be a linear space. We have a zero element, we have for each element we have the opposite of each, and so on and so forth. Everything works here.
Zero should be a scalar or also a metric?
That's what I just explained. Zero can be u. Okay? Or Orly, or anyone who wants to be there. This is the thing. The definition is abstract. It has no content, and anything that satisfies this the rules, satisfies the conditions, is a linear space. Okay. Now there are things we can prove about linear spaces only by the definition of linear space. And as I told you, these things are going to be true for all linear spaces. So, for instance, uniqueness, okay? We can prove basic theorems about abstract linear spaces just by using the definitions. So there are a few important things to know about linear spaces. So here is an example. Uniqueness of the zero element. Till now, nothing tells us that there's only one zero element. Presumably, it need not be unique. So now let's assume we have two zero elements, B and C, and prove that B equals C. Okay. So this is a theorem, right? Woof. So assume B and C are zero elements. This is an example of yeah. Assume B and C are zero elements in a linear space V. Okay, what does it mean to be a zero element? That if I take some vector V and I add to it B, I get V back, right? So take V in V. It holds that V plus B equal V plus C. V is V plus B, because that's what happens when you add a zero element, and it also V equal V plus C, so V plus B equal V plus C. Right? So now, recall that this is the definition of the zero element. It's a number 4, yeah? Is number 4 of the plus. So number 4 of the plus rules is also by number 4 of the plus rules. Existence of zero elements and the properties of the zero element.
How do you know it's the same element for different B's?
What do you mean same element? No, B is independent of it. It's not the opposite. right? I take V, and there is this property that exists zero element, and it tells you what happens with the zero element. The zero element is the one that is neutral in the plus operation. So V is V plus B. This is by definition of the fact that B is a zero element, and also V equals V plus C. This is by the fact that C is a zero element, and these two are V, so V plus B equals V plus C. No, Roman level 5 is the opposite. Now we want to impose. Okay, so by rule number 5 of the plus, we have an opposite.
You proved it?
We have an opposite. Don't have to prove it. It's the definition. We have an opposite U of V such that U plus V equal so let's decide what you want it to equal. So such that U plus V, maybe there are two different ones, one for B and one for C. It's such that U plus V equal B. Okay, so now add it here. U plus V plus B equal U plus V plus C. Now, by associativity, which is rule number 3, U plus V plus B equal U plus V plus C. Right? And U plus V, as we said, is B. In fact, we could have done it shorter, but let's go through this. You understand how everything is not, everything you think is trivial, you should forget that it was trivial. Okay? This should be explained by a rule, because if we hadn't this rule in the definition of vector space, linear space, we couldn't have done this move. Right. No.
Okay, but for rule number 4,
Yeah?
you say that B equals C, right?
You gave an alternative explanation, you might be right.
I didn't think about doing the 5 and the 12. I just would have written B equals C. I don't know if it's correct, but this is what I'm asking. B equals C, and then...
All right, from here, you'll get to B equals C?
Yeah.
Why?
If you just submit the V.
What do you mean? What do you mean subtract V? What is? There is no subtraction. I didn't say anything about subtraction.
Okay, but adding...
You can add the. That's what I did. You want to add the opposite? That's what I did. I added the opposite.
No, B plus minus...
Right. That's what I did here. Just a moment. Okay. First of all, there's no subtraction. There's a summation with the opposite, with an opposite. So that's what I did. I added an opposite here. Okay? But I don't know how to insert something to the middle. Okay? You want to put it here and then use commutativity? It doesn't matter. U is here. Even if you want commutativity, you have to first of all have this summation, and only then now you can commute them. Okay? But we don't need to commute them. This is B, and this is B. Which? Here. From here to here. Okay. So I have two vectors which are equal. Okay. Now the fact that now I can take. I have two vectors that are equal. Now I can add to them, or add them to, on the right or on the left, it doesn't matter because it's commutative, to any other vector and get the same. This is, well, it didn't go, it did, because This is the fact that it's a binary function. This plus is a binary function. What is a function? A function is something that is well defined. Yeah. If two things are equal, so add to them, apply them with some other. No, this is what it means when I say that this is a function. What is a function? The function is something you used to call a function f of x equal y, right? So now think that your function is plus. It's a binary function. Plus of a and b is some other thing c. Okay? So what does it mean that the function is really defined? That if you give it a and b, you always get c. It's not that today you give it a and b and get c1, and tomorrow you get c2. So what do I have here? I take this vector and apply the plus function with u. So I take plus of u and whatever is written on the left. And then on the right, I take the plus function of u and what is written on the right. But they are the same, so you expect the results to be the same. So that's why it's okay to take two vectors that are the same, to take another vector and add them to both sides. Okay? This is because the plus is a function. But didn't go so deep into this. Okay. This I expected you to... But it's okay that you asked about. It means that I can't get ahead very easily. It's okay. Now, what is u plus b? Is b. So we have b plus b equal b plus c. Now, what is b? B is a zero element, and under plus, it makes no change. So here, I look at b, and I say, okay, so this is by what we took. This is by far. This is by the definition of u. Yeah. The property of u. Okay. By property of u. That's how we chose this u. Now, b plus b, b is a zero element, so b, okay, because b is a zero element. And also here, b is a zero element, so b plus c is c. Okay, so we get that b equals c. So the zero is unique, so from now on, the zero is going to have a special notation. Okay, so now, it is justified just a moment, to denote the zero element by a special notation, notation. So sometimes it's going to be zero vector. And they call it the zero element from now on, because there's only one such. Your question, and then Matan.
Yeah, just two short questions about the last stage. First, were you able to say that the UV from the left equals B, and the UV from the right equals C? Then you'll get 2B, 2C, you multiply by the scalar itself?
No, then I won't go this direction. First of all, two things. First of all, I won't go this direction because I say B plus B is B, C plus C is C, and then B equals C. This is one thing. If you get B plus B and C plus C, the correct and short way to say B plus B is B, C plus C is C. Now, second of all, you have a mistake here. What do you mean when you say B plus B is 2B? When you say B plus B is 2B, it means that you assume that if you take a vector V and add the vector V to itself, it's the same as multiplying the vector by the scalar 2. Now, this we didn't prove yet. It's correct. You're right. Your intuition is correct, but see, as long as you didn't prove it, you can't use it. You can use it by proving, okay? And then again, this is, okay, and you'll have at your homework some of this. The idea is to, as I told you in the first lesson, your preliminary knowledge is bad here. Forget everything you knew, okay? What do you mean this? So you get V by rule number 5 of multiplication is 1V. Right? And then what I have? By distributivity, right. By distributivity, I have 1 plus 1 v. And so this is rule number 5 of multiplication, and this is distributivity, one of them. It was either 3 or 4, I don't remember. I think it was 4 of multiplication, and then I know it's 2v. Okay, now you can go on. But this is not, this is a theorem about linear spaces.
So, if this is not true, can you please explain again just the best stage from b plus b?
Okay, so I go one step back because Matan asked about how do I know that u plus v is b?
No.
That's what I mean? So how do I know that?
You proved only that for each v in the set of v, capital V,
Yeah. No.
all small v in the capital V,
Yeah.
you have a unique zero element.
No.
But how do you know?
No. There is no. What do you mean? No. Opposed to the opposite. The opposite has really connection to who it belongs to. The opposite of v. The zero element. Look at the definition. It's not that there is. Okay. You have to read it carefully. When I defined the zero element, I said the following. Exists a zero element for all v. And didn't say for all, this is logic, for all v exists 0. It's different. Okay? If I say there exists one that is good for all of them, like this is saying for any disease you have a cure. This is to say there is a cure good for all diseases. Okay? This is logic things we don't go too deep into, but it's good that you enforce me to go into. Okay? So when I said, I specifically specified this way. There exists a zero element such that for all v, so and so. So that's why there is no b for this v and c for another v. Now, you asked about the last stage. Okay, so from here to here, is it clear? Okay.
Defined by the rule, right?
But that's the property of u. I took u, special u, such that this be b plus b. Okay, now I look at this equation and I say this is b plus b, but b is a zero element. B, what is zero element? For any v, when you add to it v, you get v. So this is my v and this is my b, for instance. I get b plus something is this something, so I get b. Now I look at this and say, okay, b plus something is the something, so it's c. So how I get it. Okay, then again, things that seem very trivial, and some of them will be in the exercise, like that minus v is minus 1 times v. Okay? This is something to prove. Okay? It's not in the definition, then nevertheless it's true for all linear spaces, and it's something you can prove by the definitions. Okay, v plus v equal to v, we said it already.
How can you prove it if you don't have a minus v?
Right, so, that's right. So, the opposite of v is minus 1 times v, right? Okay, but this I don't use, I just want to explain. I'll state it correctly. If u is the opposite of v, then u is minus 1v. But a way to look at it is, first of all, to prove uniqueness of the opposite. So, you prove that's what you'll have to do. You'll have to prove the uniqueness of the opposite, that for every v, there's only unique u, such that v plus u is the zero element. And then, you can give, right, what I wrote earlier, minus v, is a notation. Only after you prove uniqueness, you call this element, you give it notation minus v. So minus v is a notation, the same way you had a notation for the inverse of a matrix. And then, you show that the opposite, minus v, is multiplication by minus 1. And so on. Okay, so this is for today. See you next week. It's been very fun. Happy it made you laugh. Sometimes. Okay.
Can I approach it correctly? So I got to the solution for 1C, but was it supposed to look like right? Starts at minus I.
That's what you asked me that, right?
Right. And then so what I did is I
It's
took
minus 1. No.
right minus 1, minus 2, minus 3, and then 2, 2, 2.
No, that's not a good way to write it.
Okay.
So the ith row is